Alright, ladies and gentlemen, you have reached the end of Chapter 1, the unit on transformations. You did most of that stuff last 3 days, but today we're going to look at another special type of transformation, one that's not really related to all the other ones, but nonetheless is still a transformation, and that's why they put it here in Chapter 1. Some review of terminology, because you want to be able to speak math lingo so you can talk and act like a math genius, right? So let me just quickly review some terminology that hopefully you learned in grade 10. When I give you a rule that's associating the elements of one set with the elements of another set, we call this starts with an R, E, L. Yes, a relation. Okay? Relationships, right? Connecting a boy with a girl, connecting an element to another element, right? Same idea. Now, a relation where each element in the first set is associated with exactly one element in the second, yeah, that's called a function. So, I guess in this case where you got the guy, he's only dating one girl, it's exclusive, that's a function. If he's dating two, well, he's bad news. Girls, dump him. Seriously, dump him. Guy, smarten up. Okay? Anyways, back to some math. I'm going to ask you to think of what synonyms come to your mind when you hear the word inverse. If I asked you to do the inverse, what words would come to mind? Perhaps you can go to Google right now and find out. But let's say Google and your internet is down. Well, if that's the case, you wouldn't be watching this video, would you? But nonetheless, if it was down, what would you do? How about these words? Inverse. How about undoing something? Or perhaps reversing something. Well, I think those are pretty good words or synonyms for inverse. Go ask your English teacher. They know more English than I do. So I'm going to ask us to look at investigation number 1. And let's do this activity. And hopefully this activity will bring out this idea of inverse, at least the mathematical idea of inverse. So, 2 steps. I want you in step 1 to take any number. Let's call out your input and multiply it by 2. Then step 2, take the result from step 1 and add 3 to it. Your result is the output. And it says record your results. So, let's say I took the number 1. Okay, in step 1, I'm going to multiply that by 2. So what's 1 times 2? That is 2. Then take that result, which is the 2, and add 3 to it. 2 plus 3 is 5. Here's my input. There's my output. Here's the coordinate. Let's try another one. Let's say I took the number 2. That's my A number from step 1. Multiply it by 2. 2 times 2 is 4. Take that result from step 1, add it to 3. 4 plus 3 is 7. Nice. Let's do one more just for fun. How about 3? 3 times 2 is 6. 6 plus 3 is 9. And by the way, negatives work too, I think. Negative 2. Negative 2 times 2 is negative 4 plus 3, negative 1. Okay? Now, let's inverse the previous step. So when I inverse, I'm going backwards. So instead of going forward, now I'm going backwards. That's why I call 2R, to reverse. Then I'm going to say take a number and the reverse of step 2, the reverse of adding 3 is, subtract 3. And then you're going back up. So now you've done the first part. Now you're going back up to the next part. Then it says multiply by 2, so the reverse of multiplying should be, I guess, divide. So take the result from step 2R, right from above, and now divide by 2. So let's record the results. Let's take a number, let's say 5, okay? 5 subtracted from 3, that's 2. 2 divided by 2 is 1. Let's take another random number. Let's say 7. 7 subtract 3 is 4. 4 divided by 2 is 2. Let's take some more random numbers. Let's say 9. 9 subtract 3 is 6. 6 divided by 2 is 3. See that rhythm? I've got rhythm. And this one here, how about negative 1? Let's do a negative just for fun. Negative 1 subtract 3 is negative 4. Negative 4 divided by 2 is negative 2. Okay. Here's what I'd like us to do next. I want you to graph out these points, okay? Both the results from the first part and the results from the inverse part. And let's see what we get, okay? 1, 5 here. 2, 7 here. 3, 9 here. Negative 2, negative 1 down here. Then I'm going to do the inverse ones. I'm going to use an x for the inverse ones. 5, 1, that's over here. 7, 2, that's over here. 9, 3, that's over here. And then negative 1, 2. Over here. Oops, black. Black. Well, if I look at the dots, and the dots seem to create a line. Yeah? Yeah, I think so. I can't get it to be straight. Close enough. Wait a minute. I think the x's also create a line. What if I were to put a line down the middle? Like this. Oops. That didn't look too good. It looks to me that the dots seem to be reflection in this red line, and when I reflect these dots, I get the x's. Well, remember how when we did the transformations, we looked at reflections in the x-axis, reflections in the y-axis? Here's a new type of reflection. Notice here that the dots are reflected about what line? It's not the x-axis, not the y-axis. It's about the line given by the equation y equals to x to form the crosses. So today I've just shown you that if I do the inverse process, it looks like things get reflected about this line y equal to x. Well, what I'm going to ask you to do now is, can you come up with the equation of these two lines? Okay, let's do the one in black first of all. The equation of the line in black. Remember this stuff from grade 10? Y equals to mx plus b. Yeah. Looks like the b value is the y-intercept, which is 3. M is the slope. It looks like it's 2 over 1. So y equals to 2x plus 3. What does this mean? Take a number, let's call it your input, and multiply it by 2. Then with your result, add it to 3. Wait a minute, didn't I just say these things right here? Yes, I did. Well, what about this other line in purple, which is the, I guess, the reverse or the inverse? Y equals to mx plus b. In this case, m stands for the slope. It seems like it's 1/2. The b value here seems to be, what is the b value? Hard to tell. I think it's in between, right? Probably 1.5. As a fraction, 1.5, what can that be? Well, That's the fraction 3 over 2. I can rewrite it like this too, 1x minus 3 over 2. Well, in this case, what's going on? I'm saying take a number, subtract 3, then divide the result by 2. Where did I see that before? Oh yeah, right here. Huh. So if you turn the page, what I'd like to illustrate to you is how in the world can we find the inverse of a relation? Well, if you notice, when you go back to your previous graph, you notice something about those ordered pairs. Yeah, 1 comma 5 became 5 comma 1, 2 comma 7 became 7 comma 2, 3 9 became 9 3, right? Well, the idea of the inverse is this. You want to, first of all, switch the x and the y's. Okay? And if you're doing this algebraically, after switching the x and the y's, the goal is to solve for y. Because ultimately, I want an equation. Now, how do these ideas differ? Well, they don't. Except, of course, that notation for the inverse function may be written as this. You see I switched x and y. X equals f of y. Now, notice the inverse of a function does not necessarily have to be a function. You'll see that in a moment. But when the inverse is itself a function, it has a special notation. And this notation is read f of negative 1 of x. So f of negative 1 of x. Or, more simply, they just say it's f inverse. Okay? So f negative 1 of x, sorry, not f of negative 1. I should say f negative 1. My apologies. F, and I'll say negative 1 of f of x. Yeah. F negative 1 of x, or f inverse. Okay? So here's a graphical example, first of all. I'd like you to look at the graph of y equals f of x, and I'd like you to sketch the graph of the inverse on the right, and give the coordinates for 3 points on the graph as well. Well, I'm going to take those key points. So here's one key point on the original graph, negative 3 comma 2. Another key point, 0 0. Another key point, 3, oops, not 3, 2 comma 3. Alright, well, what do we do when we do the inverse? You're thinking, let's switch them. So sure, negative 3 comma 2 becomes 2 comma negative 3 down here. 0 0, when I switch it, still becomes 0 0. And then 2 comma 3 becomes 3 comma 2. 3 comma 2. If you're connecting them together, let's see what happens. Dun, 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 dun. And you know all these points that were along 3, well, they just go vertically like that. There's your inverse. So I write this as x equals f of y, or the more general way. Actually, I shouldn't write it the general way, and I'll tell you why in a second. But anyways, f equals to f of y. Okay. All right. Let's take a look at the next part. State the domain and the range of both the relation and its inverse. So let's do the relation first of all. I look at the domain and I look and say, the x values seem to start at negative 3 and then go all the way to infinity. So I guess I can write like that. Or x is greater or equal to negative 3. The range of the relation, well, it looks like it's between the values of 0 and 3. Looking at the inverse, the domain of the inverse, well, it looks like it starts at 0 but ends at 3. And the range seems to be like the smallest value is negative 3. Notice anything here? Hmm. 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 What's this idea of inverse again? You're switching the x and the y's. I think that's what I just did. Then it says determine if both the relations are functions or not. Well, I think the first one, the one on the left, y equals f of x, that is a function. How do we know? Somebody would say, hey, look at that vertical line test. Remember that vertical line test? Draw vertical lines, only says cut and touch the graph at one spot. Oh yeah. Okay. Do the same thing with here, and oh no, totally didn't work. So is the inverse a function? It is totally not. And you can say it doesn't pass the vertical line test, or for each value of x, there seems to be more than one value of y. Okay? Because of the vertical line test showing that for an x value, that's your input, there is more than one y value. They are not exclusive. The x is dating two y's. Bad news. Okay? And by the way, that's why I did not write the inverse notation like this, okay? Because that means that the inverse is also a function. But if I write it like this, that's okay. Okay? Alright, let's move on. Well, let me show you some examples of how we can do the inverse algebraically then. And we'll also, once we've done the algebraic part, graph it out to see the inverse visually. Well, remember, to do things algebraically, our first step is to switch x and y. Now remember, the f of x is like your y, okay? So when I'm trying to find the inverse, step one is to switch x and y. I'll have now x equals to 3y minus 1. Once again, step two is just to solve for y. So I will isolate y by first of all adding 1 to the left, right? Plus 1 equals to 3y, dividing everything by 3, and there you have it. There's my inverse equation. I can rewrite this with the inverse notation. F negative 1 of x is x plus 1 over 3. Okay? Let's double check this with the graph. F of x equals to 3x minus 1. That's a graph where the y-intercept is 1, has a slope of 3. So here we go. Whee! And then the inverse graph, well, if you're not too sure, I can split this up. X over 3 plus 1 over 3. Or 1 over 3 is my y-intercept. I'm going 3 and then 1. Okay. Might be easier just to switch some points to 1 like this. Nonetheless, whee! Here's my inverse. Here's my function. And by the way, you know this is correct if I were to draw in this line, the line y equals to x, it's a reflection. So if I were to take this point, for example, 3, 8, this would become 8, 3. And notice if I draw a line here, it's a perpendicular line to this axis, the y equals x axis, perpendicular, and the distance there should be the distance there. Okay, those are key indicators to represent or know that your graph is correct and that this is the inverse of the function f of x. Okay. Try this one here. Same steps, right? Step 1, switch x and y. So x equals to y minus 5 over 2. Solve for y. Bring the 2 over, so 2x equals to y minus 5. Y equals to 2x plus 5. Once again, I can use the inverse notation, f negative 1 of x, 2x plus 5. Done. I'm going to ask you to do this with the table of values this time. Over here, if I chose the table of values of, let's say, 0 for x, 0 minus 5 is negative 5, divided by 2 is negative 5 over 2. If I chose 1, 1 minus 5 is negative 4, negative 4 divided by 2 is that. Let's say I chose like 9, 9 minus 5 is 4, 4 divided by 2 is 2, okay? Over here, if I were to choose something like negative 5 over 2, well, 2 times negative 5 over 2 is negative 5, plus 5 is 0. If I chose something like negative 2, and if you're strategic and thinking, why did Mr. Lee choose those values? Hint, hint, hint. Hint, hint, hint. The x's become y's and the y become x. 2 times negative 2 is negative 4 plus 5. That looks like it's 1. And if I do one more, 2 times 2 is 4 plus 5 is 9. Okay? I'm not going to graph this out because I can see from the table values this definitely is the inverse. I feel happy. I'm going to move on. If you don't like it, go back and graph it out. Okay, one more. How about determining the inverse of a quadratic now? F of x equals to x squared minus 4. Then graph both the equation and its inverse on the set grid. I'm actually going to graph out the function first, okay? F of x. If you want to make a table of values, you can. Don't need to, by the way. Negative 2 squared is 4, 4 minus 4 is 0. Negative 1 squared is 1, 1 minus 4 is negative 3. Oh yeah, we've seen this graph a few times. Hope you're used to drawing parabolas by now. It's been like 2 years. Okay, now, how do we algebraically determine the inverse? Okay, let's find the inverse. First step is to switch the x and the y. Remember that? X equals to y squared minus 4. Next step, solve for y. So I'm going to add 4 to both sides, x plus 4, and this equals to y squared. I got to get rid of that square, so I'm going to take the square root. Be careful when you do that, because you better put a plus or minus in front. Okay? And if I now were to make a table of values for this, let's say I chose x is 0. 0 plus 4 is 4. The square root of 4 is 2. It's now plus minus 2. If I chose something like negative 3, negative 3 plus 4 is 1. The square root of 1 is 1. It's plus minus 1. Negative 4. If I chose that, negative 4 plus 4 is 0. Square root of 0 is 0. Plus minus 0 is 0. Well, let's graph these points. 0 is 2 and also negative 2. And negative 3 is 1 and also negative 1. Negative 4 is 0. Can you see a graph that looks like this? Now, once again, I'm going to draw out that reflection line, but can you see how this makes total sense? And how the blue actually is a reflection? Sorry, the purple graph is a reflection of the blue? There you go. It works. Now, as one last thing for this section as an extension, it seems like this is actually, or the inverse, that's the graph in purple, doesn't really look like a function, does it? Well, my question to you is, how could I restrict the domain of the original function so that the inverse also becomes a function? Now remember, in order for something to be a function, it has to pass the vertical line test. It has to be where for each x value there is only one y value. Watch me draw vertical lines. Oops, 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 right? 2 values. So what do you think I can do? Oops. What do you think you should do to try to make them functions? If you're thinking, Mr. Lee, why don't we just keep 1/2 of that sideways parabola? Yeah, let's keep the top half. Sure. If we were to keep the top half, and I'm going to draw this out for you here, okay? So if we were to keep that top half, which half of the original parabola do we actually keep? So once again, here's the vertical line. Which part do I keep? Do I keep the left part or the right part? Yeah, I actually keep, and if you do the inverse of this, right? -4, 0, 0, -4, -3, 1, that's 1, -3. You've actually kept the right side of the original parabola. So what you could do, solution number 1, is to keep the right side of the parabola. And if you do that, the domain of the original function would then be x is bigger or equal to 0. And that leads to, the inverse being only the top half of the sideways parabola. And if you're curious what the equation would that be, well, you're keeping the top half, that's the positive one, so just positive root x plus 4. That's solution 1. Wait a minute, there's also solution number 2. What's the solution for number 2? Yeah, let's keep the left side. Well, once again, the inverse you'd keep would be the bottom part. And this translates to the left side. Right. Yay! Domain in this case then would be to x is less than 0. Okay? And then therefore you keep the bottom half of the inverse or the sideways parabola, and the equation would be the negative. Okay? And remember, the negative makes sense, right? Taking the negative, it's reflection in the x-axis. Isn't it great how everything comes back together? All right, we're done.